Good morning, happy Friday. Thank you everybody for coming. The exams will be returned on Monday after class, and it was a challenging exam, and I think the class did quite well. The average was 68, median was 70. We're going to wrap up the discussion from the video on Wednesday on differential scanning calorimetry, and really the DSC trace with the TG curve, or sorry, the TG transition, crystallization transition, and the melting transition all sort of represent a different part of the rest of the course. So we're going to talk about polymer microstructure, so the arrangement of molecules in the glassy region, in the crystalline regions, and how those properties combine to create the mechanical properties and thermal properties of the bulk materials. So it's worth keeping this graph in mind. And this is a typical DSC trace. By typical, I mean highly idealized. And what we do is plot heat flow versus temperature. And remember, there are two pans, one that has a sample in it and one that has either no sample in it or a sample with a known heat capacity that undergoes no thermal transitions. And as you add heat to as you increase the temperature of both pans, it might take a different amount of heat in order to raise the temperature of the sample compared to of the blank pan. And the amount of heat that you pump into the sample will be different depending on whether or not there is an exothermic or an endothermic transition in the material of interest.
Professor?
Yeah.
How do you actually account for the amount of heat you pump in? Is it just stoichiometry of the fuel that you're burning? Or?
Not fuel that you're burning, but how do you calculate the amount of heat that goes in? If you're heating it up using a resistive heater, then you know how much heat the resistive heater gives us off based on the amount of current that you put in. So in almost any analytical equipment, you're almost always measuring current, which is one of the quantities in a laboratory that you can measure the most accurately. So even in a balance, you're not actually measuring mass, you're measuring current. You're measuring the current it takes to levitate the pan using an electromagnet. So even in scanning electron microscopy, you are deflecting a beam with electromagnets, and you're doing that with current. So current is a really important quantity because we have the ability to measure it so accurately. Whenever you see the y-axis in heat flow, you always have to specify what direction is into the sample and what direction is out of the sample, and usually that just corresponds to some statement like heat flow into sample that is endo up. So endothermic transitions will be up. And just by way of review, you start out, say, somewhere here, then there's a transition where the slope of the line changes, which corresponds to the glass transition temperature. Then we have an exothermic peak and an endothermic peak. And this is for a semicrystalline sample. And this temperature, where the heat capacity changes, so the slope of the heat versus the temperature changes, that signals a change in heat capacity, is the glass transition temperature. The exothermic peak is the crystallization temperature. And the endothermic peak, the last peak, is the melting temperature. So why would crystallization be an exothermic transition? So remember, forming bonds or forming better bonds gives heat off. Forming better bonds gives heat off. So if you go from a glassy state, which has poor, like low density, because your molecules are not packed to their maximum extent, and then they pack really well, they're getting closer, the bonds are stronger, that is, the van der Waals bonds are stronger, and heat comes out. And that's really a take-home that I'd like you to take from this class. You know, one of 10 intuitions I'd like you to bring to your future scientific and engineering lives is that bonds give off heat. Favorable interactions being manifested, favorable electrostatic interactions manifesting as bonds gives off heat. Because by conservation of energy, where is that potential energy going to go? Okay, so semicrystalline samples. This would be like atactic polystyrene, right? No. It would be like isotactic or syndiotactic polystyrene. If it's a completely disordered molecular structure, it's not going to form crystallites. And the only thing you would get here is the TG, not the TC or the TM, which are only related to the crystalline regions of the film. Okay, we prepare these samples in order to get the best chance at getting strong transitions. What we try to do is start with an amorphous glass. So what you typically do to prepare the sample is to heat it up past all the transitions and then cool it rapidly, which is called quenching. So you have a plate of frozen spaghetti so that when the TC appears, it's a strong the glass transition appears, it's a strong transition. TC appears, it's strong, and then after you crystallize, you melt again. Okay, any questions about DSC before we move on to a discussion of the melting temperature and crystalline regions?
Just to clarify, on the DSC curve, is glass transition temperature at the beginning of the upwards, or is that in the middle of it?
There's usually some overshoot here, and this can be for a number of reasons, but if you want to be, this is generally what you see, but if you just had this, it would be the same thing. TG would still be here. TG occurs over a range, and there's usually some thermal artifact that appears around TG that corresponds to this sort of bizarre shape. Yeah.
In the molten state, we have all amorphous?
In the molten state is all amorphous, yeah. It's like a liquid. Okay, so let's look at the crystalline regions. Now, a couple of years ago, first time I taught this course, I brought in some pencil leads from a mechanical pencil and a laser pointer, and I turned out all the lights and I tried to do Young's double slit experiment on the blackboard. And because you need to hold the pencil leads exactly the right distance apart, it's very difficult to do. It's easy to do this in the quiet of my office, and I'm like, oh, that'll be a great demonstration. But then when I came in and had 100 people staring at me, of course, it didn't work. So you'll have to take my word for it that if you have a mechanical pencil leads and you have a laser pointer, you can do this experiment at home and impress all your friends and show the wave nature of light. Well, how is that related? Well, how do we measure the dimensions of the crystallites in the solid state? So we know that light diffracts when features that it's interrogating have characteristic dimensions on the same order as the wavelength of interrogation. So in polymers or molecular dimensions, we're usually talking about X-rays. So if you shine X-rays through polymer pencil leads, then you get a diffraction pattern on a screen. And based on the distance and the angle between the diffraction peaks, you can calculate by Bragg's law the distance between features in the polymer crystallites, which can tell you about chain dimensions and the microstructure. So this will be the primer on diffraction. So suppose you have some molecular rods that are oriented like a bundle of sticks that are one right behind another. It's a horrible image. Anyway, they're a bunch of cylinders. And you get a beam, you get the transmitted beam, and you also get diffracted beams. And if you have a detector, which is like a screen, much like this screen, you have some peaks that appear, some diffraction pattern that appears on the screen, where this is n equals 0, and then n equals 1, n equals 2, n equals 3. The 0 is in the middle. Okay, similarly, and this would be, so these are polymer chains. And this whole thing, let's say this is a crystallite. As opposed to crystal light. Maybe they don't make that anymore. I didn't hear anyone say they do, so clearly they don't.
They do.
They do?
Yeah.
Thank you. Phew. Okay, if we have the cylinders stacked this way, and they're like bowling pins, right? There are many in front and behind each other, but they're stacked perpendicular to the axis of the incoming beam, H nu, and these are X-rays. Actually, that would kind of be a cool way to defeat the X-Man Cyclops. If he blasted his eyes at you and you just hold up some pencil leads and they diffracted around you. I'm gonna sell that to Magneto. Okay, now what if the cylinders are oriented, almost done. What if the cylinders are oriented parallel to the incoming beam? And I can't draw it up here, so I'm going to draw it down here. You get some kind of pattern like this. Okay, one more scenario. What if you have a bunch of flat crystallites where the molecular axes are oriented parallel to each other and parallel to, say, one axis of this crystallite? So it's like playing card. It's like a bunch of playing cards or diffraction gratings that you're shining an X-ray through, but the diffraction grating has molecular dimensions. Now and suppose that there are a whole bunch of these, not just 4. What type of pattern do you suppose you get on the detector in this orientation? You get concentric circles of different intensities. Okay, so what if you have a totally amorphous sample? So no crystallites. You get no diffraction. And then we'll get out our Bob Ross smudge stick here. You just get solid signal and no differentiation. Okay, that's all I want to show. So a couple things. The angle corresponds to the size and spacing of the features. And the smaller angles correspond to the larger features. A little counterintuitive, but the narrower you hold the pencil leads, the wider the diffraction beams, the wider the diffraction pattern is going to be. And the sharpness of these peaks. So they're not really going to be like perfect lines unless you have a perfectly crystalline sample, which in polymers is damn near impossible to do. So what you're going to end up having is some fuzziness where the intensity is going to be a bit like a Gaussian curve. So the sharpness corresponds to the size and the order. Say order and regularity in the crystal structure and to the size of the crystallites. Okay, this is all well and good for bulk samples, but what about for thin film coating? So often in photoresist features, so those are photosensitive films that you put on a silicon wafer when you're doing semiconductor manufacturing, or if you're doing thin film photovoltaic work, or even like Scotchgard coatings and stuff on glasses and optical equipment, which are often polymeric thin films. We can't just shine a laser beam through a thin film that's only like 20 or 100 nanometers thick because we won't get enough signal to detect anything. So in that case, what's done is a technique called grazing incidence. X-ray diffraction. And this is for thin films. And by thin films, I mean a few nanometers to a few microns. And this is called GIXD. Now, it's possible to do these experiments with a lab scale X-ray diffractometer, but it takes forever to get enough signals. So often what people do is they apply for beam time at one of the national labs that has a synchrotron source, which is a very high intensity X-ray laser. It's like basically is like a particle accelerator. It's a giant facility, and you take beams that come off of the main beam line to give you these highly coherent X-rays. So it's like a really powerful X-ray laser, and you can get these diffractograms really quickly. Whereas even though you have to apply for time and wait like a few months to get time sometimes, you can get more information in like a day than you can in weeks or months of doing using lab scale equipment, if it's even possible to get the information using lab scale equipment, which sometimes it isn't. So the typical setup, you have some reflective substrate, which is maybe like a silicon wafer. And then on top of it, you have your polymer film of interest. And you have some detector over here, which is like a movie screen. And your high intensity X-rays come in at an angle of just a few degrees, and then they bounce off the surface and they generate a diffraction pattern on the screen. And they're going to be symmetric here. This axis is called the QZ axis, and this axis is called the QXY axis. And one material here, depending on its surface texture, and the texture literally means the orientation of the crystallites. So we can't necessarily feel that texture, or can we? But it has the same. It's sort of analogous to the texture of a floor. So let's look at an example of the signals that you might get from a GIXD experiment. And let's pick a polymer that has some kind of hierarchical structure in the solid state. And this is, we saw this before, this is a polyhexyl isocyanate. Now, one of these chains, and this is called a comb-like polymer. And I drew a rectangle around it because you can kind of see that these polyisocyanate linkages are pretty rigid, and they have these alkyl chains that come out, these hexyl chains that come out. So let's say that for simplicity, we're going to draw this as a 3x5 card we're going to approximate it as a 3x5 card with lines in it where the lines are these. Is that okay? So we can kind of see what's going to happen here. So if you look at the texture of the film, suppose you have Suppose you have a texture where the playing cards are lying flat, and you shine the laser beam, the X-ray laser on it, and it's going to bounce up, and on your detector, it's going to give you features in the XZ direction. You can do this at home, again using a laser pointer. Be careful with laser pointers at home. And your phone. So if you take your phone, and your phone has nanometer scale films in it, not of polymer, but of indium tin oxide and glass and color filters for the LCD display, and you take a laser beam and you do grazing incidence, literally, you shine it as a grazing incidence, and you turn off the lights, you'll see a diffraction pattern in the, on the wall from the features in your phone. And you'll see them in the XZ direction. You'll also see them you'll see them in the QZ direction. You'll also see them in the QXY direction. The ones in the QXY direction are because of the pixels. So because you're getting diffraction off of the pixels that are arranged in the display.
What are the 3 planes again? The 3 fire. Yeah, the 3.
Oh, these are this thing on its side. 3 of them. So because of this stacking, you'll get this pattern. But suppose, and this is a face-on texture. But you could also imagine having the cards You could also imagine the cards oriented in such a way that when they diffract in the XY direction. And this is called the edge on texture. And of course, if you had a mixture of face on and edge on, you'd get both signals in the QZ axis and the QXY axis. Yep.
Which way are you have the lines in the 3x5 card you mentioned?
Mm-hmm.
Which way are those oriented in each of our stacks here?
Yes. So those will also give you diffraction patterns. So I didn't draw these, but if they're all oriented the same way, then you will get peaks out here in the XY direction. I didn't want to complicate matters because I'm about to complicate matters. Let me complicate matters and we'll see if that makes things clearer. Yeah.
Does each card correspond to one molecule of that chain?
It corresponds to one or a group of molecular chains in a crystallite. So really, I drew just 4 repeat units here, but you'll have them below and below and below and longer too. So yes, the molecular chains, the chain dimensions will also diffract, not just the lamella, they're called lamella. Yep.
That actually works best when we have more of a crystalline structure rather than a mix of both amorphous and crystalline?
Yes, diffraction works best. It only works in crystalline regions. So if you have a bunch of amorphous stuff, you'll have noise in the signal, or you'll have just, it could overwhelm the signal depending on the ratio. Okay, so let's imagine a 3-dimensional space where we have a bunch of these lamella that are themselves composed of these molecular chains oriented thusly. And we shine light through, we'll have diffraction that corresponds to different chain dimensions. So this axis is the lamellar stacking. This is the chain axis. So you'll get diffraction along this chain. You'll get very wide angle diffraction here because you'll have diffraction between each one of these chains, which goes back to Ryan's question. And through this stack, but of course you have to angle the X-ray beam in such a way that it will diffract. Because if you just shoot through a plane of playing cards perpendicular, you won't get any diffraction because there's nothing to diffract off of because it just sees one uniform block of things that repeat. There's no angle dependence. There's nothing for it to diffract from. So in this, so this is, one second, this is adjacent stacking in this axis. And oftentimes, if you have a material that's flat, like polyalkyl isocyanate, and it's flat because you have pi bonds here and to a lesser extent here, sometimes this is called the pi stacking axis, just like in DNA. So sometimes this is the pi stacking axis. Yeah.
Are we still talking about thin film grazing incidence diffraction?
We're talking about this is relevant to all forms of diffraction. But each feature in the molecule, in the crystal structure, the distance between this one and this one, or between this lamella and this lamella, are going to diffract. Then the next smallest order of diffraction is going to be the distance between these stacks, and then the smallest one is going to be this distance between the monomers. But the largest size scale of the features will produce the smallest angles by Bragg's law. So everyone see how there's 3 different ways that a structure like this can diffract? Of course, if we didn't have these side chains, it would be a lot simpler. We would just have these crystalline rods that could either be oriented toward the beam or perpendicular to the beam, either this way perpendicular or this way perpendicular if the beam's coming in this way. Yep.
So by polymer, you mean that the carbon chains, like all those lines in the box,
Mm-hmm.
boxes in the graph are carbon chains,
Yes.
like in the drawing?
Yep.
And there's repeating.
Yep.
Making sure.
Yep. Okay, so let's use Bragg's law to quantify some of the features. So we have a source, we have a monochromator, we have an incident wave vector k0 with magnitude 2 pi over lambda. We have a sample, we'll just say it's a cube. This is for bulk X-ray diffraction, but for grazing incidence thin film, the principles are exactly the same. Anybody taken Nano 106? How about any other material science course where you've seen, well, everyone's seen this at least in physics. So if you're interested in learning more about X-ray diffraction, take Nano 106. Okay, so we have a diffraction angle theta. This is the transmitted beam. And this is the refracted beam. And this is the detector. And this is the scattered wave vector k. And the wave vector change is given q. And in vector notation, it would just be k vector minus k naught vector. With angle theta between.
Professor?
Yep.
When you say wave vector, are we treating it like a ray?
Like a what?
Like a ray? Wave vectors versus rays. I think it's just terminology difference.
Yes. So this is the so the wave vector change q is also called the scattering or momentum transfer vector. And it has magnitude q equals 4 pi over lambda sine theta over 2. And the scattering intensity is monitored as a function of scattering angle. And by Bragg's law, we have the order of the reflection equals 2 times the distance d between the crystallographic planes that we care about. And the crystallographic planes could be any one of the 3 types of size scales that we're talking about over there, or any one of the 2 in the case of straight chain polymers versus comb-like polymers. So n lambda equals 2d sine 1/2 theta, where n is the order of the reflection. Order of the reflection, where the one in the middle is n equals 0. D is the distance between crystallographic planes. Or scattering objects. And sometimes we make the substitution to calculate the spacing from the scattering vector q. The relation is d equals 2 pi over q. And we call this d lives in a real space. And q is in q space, much like the q continuum. So an X-ray has lambda, just so you know, of about 0.15 nanometers. And remember, we can only diffract off things that are in the rough area of the wavelength with which we are interrogating them. So if you use a monochromatic X-ray, you'll get, it'll be about 0.15 nanometer wavelength, which is commensurate with atomic scale distances, and or atomic and molecular scale distances, and then you'll get the information that you want. But the angle of refraction will be totally different depending on the size scale. And why does that matter? Well, if you're probing, why couldn't you just get all the information in one shot, from the lamellar distances to the to higher order distances? Suppose you have block copolymers that have several microns between spaces, or maybe a micron or 500 nanometers or a micron between spaces. You'll get very narrow spacing, right? Because big features give you narrow spacing. I mean, big separation between features give you narrow spacing. But then what if at the same time you also cared about the molecular dimensions? So you wanted to know the distance between molecules and between polymer chains. Could you do that on the same equipment? It turns out that you can't. And in some cases, it's just a function of the fact that the room you're in for small angle X-ray scattering for big objects isn't big enough for the screen, the detector that you need to get wide angle stuff. It's not quite that simple, but you can't just collect whatever information you want from exactly the same lab, because it's not set up to collect beams that are refracted over such wide angles. So just as a point of nomenclature, small q values means small scattering angles. And therefore big Ds. And these could be block copolymer structures, and we'll talk a lot more about block copolymer structures in I think next week. Chain dimensions, and aggregate sizes. I mean the dimensions of the entire chains, not the dimensions of the spacing between monomers. So for small scattering angles, we call this, it's called SAXS. Really should be pronounced SAXS, but it's just SAXS. And for SAXS, we have D is greater than about, say, 10 nanometers, and your theta angles are greater than, say, 10 degrees. Large Q values are a consequence of small d's. So d's less than about 10 nanometers, and scattering angles theta of greater than about 10 degrees. And what does this give you? So this is a wide angle. Or WAXS. What you get here is a crystallite structure. So this information would mostly be obtained by WAXS, not SAXS. Local conformation. Orientation. That is orientation of crystallites in the way we've been describing. And texture. So most of what we've been describing is actually in the WAXS regime, and that's mostly what we'll care about. Yeah.
For the SAXS, does the theta that you put theta less than 10 degrees?
Yes. Sorry. Yeah. Small angle, theta less than 10 degrees. Now, what does a typical diffractogram look like? You plot intensity versus theta, or sometimes you plot it in Q space in units of inverse angstroms. And for a semicrystalline sample, you might get some peaks that look like this. Or for an amorphous sample, you would just get this.
Is that graph for angle scattering in general, or is it specifically for like SAXS or like WAXS?
It's in general. It could be for either. And also be careful about how theta is defined in the polymer community. It's defined as I've defined it, but in optics and physics textbooks, sometimes it's 2 theta. So just be aware, it doesn't really matter, but just make sure the diagram and the equation matches up. We're going to talk about specific types of conformations in polymeric samples and how these polymers exist as crystallites on Monday and next week. So have a good weekend. Thanks.